Today's webinar is on simplifying stats for A/B testing. And the agenda behind this webinar and this idea is that I think statistics has been really confusing for experimenters, and it's really time that we start to simplify it, because through my research in statistics, I've realized that there are some common confusing points in statistics that make it very hard. But apart from that, once you start grasping it, it's not that hard. So in this webinar, I'll be going over three things majorly. Firstly is to set the MD in the start of the test so that you are aware on what sample size your test really needs. And then we'll be moving on to the statistics that you see in your report and what do they mean. So I'm wanting to share with you a simplistic model to understand what each statistics mean. And finally, we'll be moving on to statistical decision making. So quickly getting started with it. Firstly, a short bit about me. I'm Ishan Goel, and yes, just a second. A short bit about me. I'm Ishan Goel, and in the past 4 years, I've been leading product and research at VWO. So I've built the new stats engine for VWO. I've also been involved in writing and speaking regularly about A/B testing. So I've been writing a blog called VWO Stats Blog. I haven't been writing it for the past few months, but I put a lot of articles there. Finally, I've been talking to a lot of customers and solving their problems. So that's my source of understanding on what are the most pressing problems of A/B testing today. And finally, I've been learning and reading through books, through courses, and a bunch of other places. So that was a little bit about me. Moving on to the webinar. Firstly, we'll be talking about, as I shared, estimating sample sizes for your test. So estimating sample sizes is very important before you run the test so that you have an idea on how much traffic your test gets. And further, for estimating the sample size, you need to know what is the MDE and how to define the MDE. So I'll be starting with that and the knobs that you need to set the sample size right. Then we'll be moving on to 4 levels of statistics, where I am breaking it down that from the data that is collected in your test to the final statistical significance, how everything is into a logical framework. Finally, I'll be talking about Twyman's law, and Twyman's law is essentially the idea that whenever you have a surprising result, you should scrutinize it strongly to understand that if there is a mistake or not. So we'll be covering 7 questions that you should ask every time you get some results from an A/B test. So moving ahead quickly. This is the first thing that I want to share with you. I shared this post on LinkedIn as well. Why I am sharing this with you is because I feel that the major source of confusion in understanding statistics comes from this idea that there is a true improvement in statistics that is sort of the population average, which is something that will never be knowable. So if you run your test and say you make some change X, that change X will have a true impact on the entire set of your population. And that true impact will never be known because your entire population includes people who might have who might be even in the future who have not accessed your website yet, and the entire subset of people who have been to your website and are going to be. So theoretically in stats, the true statistic value is never observable. What you can observe is that you can only collect a finite sample in a fixed time period. So you can observe the sample mean that you have collected in a time period, and that sample mean sort of revolves around the true mean. So I want to explain this with an intuition of the pendulum. So if you imagine like 2 pendulums are hanging from a rod, and the distance between where these 2 pendulums are hanging from is the true improvement that is unknowable. And now these pendulums randomly sort of fluctuate around their separate means. So like control has a mean, say the true mean of control is 10%. So you can expect to see anywhere around 12% or 8% or 9% or 11%, and similarly with variation. So the sample means tend to fluctuate around the true means, and that is the source of big confusion in A/B tests. What you are able to observe is only the observed improvement. And as you collect more and more samples in the test, this swing sort of settles down. It never stops entirely, but in the starting, it's large. These sample means sort of deviate a lot compared to the true mean. And as you move forward, they settle down, giving you a clearer picture of the true improvement. Anyone has a question about this core intuition, they can ask it right away. And I'm happy to help. You can just unmute yourself and yeah, ask the question if you have any, or you can drop in the chat. Great. So I'll move forward. Now, the first thing that you need to do in any test, which sort of often gets overlooked, it has not been properly advocated, at least in the modern A/B testing framework, is you need to have an initial idea on how much sample size you need. So essentially, you need to understand that how much sample size will it take for that initial fluctuation to die down, to converge essentially, so that you have some confidence in the results. So starting with the sample size, I want to share that what determines the sample size of your A/B test. And while you might be hearing about a lot of parameters like the MD, the statistical power, the false positive rate, essentially there is only one parameter that's the most important. You can play around with the other two as well, but I want to give some time to talking about the minimum detectable effect. So the minimum detectable effect, which is popularly known as the MDE, that essentially defines that what is the minimum effect that you can detect from a test. So suppose I have 100,000 visitors available for with me to run this test, then there is only a minimum amount of effect that I can detect in 100,000. So like say my MD is 5%. So essentially what MD says is that a difference smaller than 5% you will not be able to detect in 100,000 visitors. Sort of. So in probabilistic terms, I'm going by the rough definition. Essentially, the idea is that if I'm investing these many visitors in the test, I want to be able to detect a minimum of this effect size in the test. Anything larger than the MD will be detected in the test, but anything smaller than the MD will not be detectable in the test. So first, let us build a slight intuition about MDE. And what I really like to show people is this thing essentially that people generally have this question that why a smaller uplift requires more visitors in a test, and is generally counterintuitive to a lot of experimenters when they start off. I like to show them this picture, and then it becomes immediately clear that so the question in this picture is we have three rows. We have A, we have B, and we have C. And my question to you for each row is that which of the shape, the right one or the left one, is the bigger one in the three pictures? So you can take 2 minutes to think through this. I don't think it'll take very long for you to get the idea. So essentially, what I'm trying to highlight here is that you look at A, you are very quickly able to tell that the yellow circle is bigger. You look at B, it takes a slight while, but you are still able to tell that this purple one is bigger. But when you look at C, it takes a lot of time to guess which is bigger, probably the longest. And that's what happens with statistics as well, that when differences are small, then statistics needs to be much more sure in declaring a winner. And that's why once you define the MD, anything larger than the MD is detectable within that given sample size budget, but anything smaller than the MD is not detectable in that budget. So any questions up till now on that part? Thank you, Kishle. So any question, any confusions, any sort of yeah, misintuitions around this? Great. So I want to highlight another thing that matters, and that is so MD in its absolute terms. So the minimum effect does not matter. So what matters is what is the minimum effect with reference to the fluctuation of your sort of pendulums. So standard deviation is represents the variance in your metrics. So if your metrics fluctuate a lot, then even detecting a large difference in them will be hard. But if they fluctuate a lot less, then even detecting a smaller difference is easier. So what really matters for sample sizes is this ratio of MD by standard deviation. If your metrics, if your metric sort of fluctuates by 2% and your MD is sort of 5%, then it is easier But if your MD is 5% and your metric fluctuates by 10%, then it's much harder to detect the difference. And this is the standard idea that you should have in your mind. Naturally, you'll get sample size calculators. Like a very good sample size calculator that I use is Evan Miller's sample size calculator, where you can just key in the values. So I'll quickly tell you how you can use this calculator as well for sample size calculations. So this is Evan Miller's sample size calculator. It has come in very handy for me for a lot of past years. So you just need to Google search Evan Miller's sample size calculator. I'll even paste the link in the chat for anyone who needs. Um, and this will tell you how like basic sample size calculations can be done. So essentially, you need to define your baseline conversion rate because MD is always counted as relative to whatever is the baseline average. So if you have a baseline revenue, so suppose your metric is revenue and your baseline revenue is $10, then a 5% MD means $0.5. So here you have the option to sort of tell it whether you are referring to absolute difference. Like in absolute difference, then 5% over 10% sort of becomes 5% to 15%. So that's the absolute difference. And in the relative difference, the 5% is sort of 5% of 10%. So it's only 0.5% on both sides. So essentially, MD is symmetric on both sides. And in this test, within 56,000 visitors, you'll be able to detect a variation if it has lesser than 9.5% conversion rate or more than 10.5% conversion rate. The gap between, like, so very small uplifts between 9.5 to 10.5% won't be detectable within these sample sizes. So you can play around, you can set an MD to your test, and this will tell you the requirements. Any questions on calculating this? If there are detailed questions, okay. Vaitis has a question. How do you determine MD relative to the baseline? Should it be built on intuition and business knowledge on what moves the metric? So yes, Vitus, I hope I am pronouncing your name right. There are two things. One is MD relative to baseline is more stable. You just generally people start with somewhere between 1 to 5% relative, but the thing is that it is like dependent on the past experiments that you have run. So you start with a conservative value, and as you go on running more and more experiments, you sort of get an idea about different metrics, that what sort of an uplift you can expect in these. So it's a trial and error process. The maths is very simple of it, that you take the baseline conversion rate and 10% of 10%. Like for here, in this case, the relative is sort of 10% of 10%, which is 1%. So if there is any doubt on the multiplier aspect of it, I'll you can ask me separately and I'll explain mathematically. Derek has a question. Thank you, Derek, for asking. How do you do this for ratio type metrics like purchases per user or views per user? So on ratio type metrics, essentially, so ratio type metrics, what you are referring to is what we generally refer to as continuous metrics. So that do not have a 0 or 1 value, but rather can take multiple values, like purchases is 1, 2, 3, 4, or on a continuous scale. I think I'm understanding it right, Tarek, your question?
You are indeed, Ishan. You are indeed.
I'm sorry?
You are indeed, yes.
Yes. Okay. So, the how is this measurable for continuous metrics? It's a very good question. The thing is that the baseline conversion rate becomes the baseline average in that case, which is very straightforward. But one other important parameter comes in that generally calculators don't give, and that is the standard deviation of the metric. So, this very important point to know is that sample size calculations for conversion rate type metrics do not need this extra parameter of variance, because variance is a function of the baseline conversion rate. But for continuous metrics like purchases per user or views per user, there'll be an inherent fluctuation in purchases and views that we call the standard deviation. So we need to measure it from data. And then then it's just a straightforward formula. We practically just divide the MD by the standard deviation. Does that answer your question, Derek?
It does. Thank you very much.
Yes. You're welcome. You're welcome. So Pierre has a question. Should I calculate the standard deviation of my KPI before calculating my MDE? Should this value play a part in the choice of my KPI? Yes, both answers right. One is that yes, you need to have an idea of your standard deviation. Generally, people have this when they're tracking their metrics, like outside the test. When they are not doing that, we use the first 500 visitors in the test to calculate the sample size. But it's very good to have an idea of your standard deviation before starting the test. Secondly, if the standard deviation is high, then you do need to sort of do some changes to your KPI metrics. Either you choose some other KPI metrics or you transform them to reduce the standard deviation. So we'll talk about them more in detail, probably not in this webinar, but some other webinar. But by controlling the outliers and stuff, you are able to reduce the standard deviation. Any other questions anyone has up till this point? Great, great, great. So I'll move forward. I have now two questions for you to make this a little bit engaging. So if anyone wants to take a guess, they can. The first question is pretty straightforward, but suppose you are running a test on engagement time and past winners on this metric on similar pages have shown a 3 to 6% uplift and sometimes a few times larger as well. So what would be a good MD value to set here? Anyone wants to take a guess, either in chat or they can speak out. Interesting. I'll share the answer. Essentially, the MD should come on the lower end of your expectation, not the median or average of your expectation. Because if you are running a properly sequential test, and even if you're not running a properly sequential test, you'll be able to detect an uplift larger than the MD, but never an uplift lower than the MD. So ideally, you should place it towards the lower end. In this case, I would want to place it towards 2 or 3%. So that's one thing. The second question that I have is, and this is to understand like what happens when you get an uplift smaller than the MD. So I've been saying that you cannot detect it, but it's not exactly like that. Now in this sample report, what I've given is that the MD was set to 5% and the decision threshold was 95% and the maximum required sample size was 100,000. Now, suppose at 99,000 visitors, you are able to see an uplift of 4%. What do you think roughly the statistical significance would be around? Like, will it be greater than 95%? Will it be less than 95%? Will it be much lower? Anyone wants to take a guess? Less. Darek is right. Vitus is also right, 90%. If it was, yeah. So basically, the idea here is that if you have an uplift that is smaller than the MD, then it is not like it won't be detected. It is just that it is likely that it will not cross your threshold of winning. It might be below the threshold of winning, but it will be closer. So had the uplift been 2% or 3% here, it would be much lesser. But since the uplift is very close to the MD that we set, so it's sort of like the statistical significance might be something around 90, 95 or 85%. In this case, I sometimes recommend that you can sort of increase the test duration by lowering the MD. It is okay in some scenarios because you are running the test longer to see if the 4% uplift reaches significance or not. Any questions around this? Great.
Is that
Yeah.
Ishan?
Yeah.
Forgive me if this is a stupid question, but that sounds a little like peaking, sort of.
Yeah, so essentially that does sound like peaking. So I recommend it in very spared out scenarios, and I apply a deliberate cutting of p-value limits after that. So I definitely understand it is peaking, but what we have now been doing and how we have evolved the stats engine at VW is that we control for peaking. So we correct the probabilities for peaking. So if you're using a sequential testing engine that is properly corrected, then you are allowed to peak. Does that?
It
Yeah,
does. Sorry, I hadn't joined the dots with sequential testing. Thank you.
interesting. Okay, great. So now coming to the 4 levels of statistics, and this is my most interesting part of this webinar. So I'll share that with you. What I'm trying to do here is that I'm trying to break down the statistics that you see in your report into 4 logical levels, which has been so hard to understand because of the definition of p-values. But before I come to these 4 levels of statistics, I want to explain the difference between Bayesian versus frequentist in a very simplistic way, because the 4 levels that I've defined are from the Bayesian school of thought. So anyone who has studied p-values from the frequentist school of thought might feel that this is entirely something different and something wrong. So it is not. I'll explain the difference. Firstly, very basically, if you see this picture here of the pendulum swings and where the true improvement on the observed improvement is, without going into detail, what I want to share with you is that when frequentists talk about statistical significance, they talk about the probability of what has been observed. And when Bayesians talk about statistical significance, they talk about the probability of the true improvement on what is possible. So this is the fundamental difference. But what we have found through a lot of research is that in certain scenarios where non-informative priors are used, uh, frequentists and Bayesians have exactly the same output. So I'm not going into details. That's a separate webinar I'll be holding about Bayesian and frequentist. But why I'm sharing this with you here is that uh, so frequentists use something called a t distribution, and on the t distribution, the x-axis represents what has been observed. So the mean of the sample that has been observed and the standard deviation or standard error of the sample that has been observed. Whereas what Bayesians derive out of this is that they talk about the true mean that is plausible, and like the x-axis has different possible true uplifts that you can infer after observing the data. So I am going to be sharing my 4 levels from the second school of thought, but they almost map out to the same p-values and to the same probabilities. It's just that Bayesians, I feel, make it easier to understand these. So I request you all to keep the difference aside for a while. We can definitely discuss the difference at length and where these two do not match. Currently, I would like to share, keeping the nuances aside, a simple way to understand the 4 statistics that you see in the reports. Anyone has questions on Bayesian and frequentists or anything? I'll just quickly see. Okay, great. No questions. So talking about the 4 levels, the first level is the empirical data that we see in the reports. So suppose you run a test and sort of you get 500 converts out of 5,000 visitors on control and 600 converts out of 5,000 visitors on deviation. Now, the thing about this is that these empirical numbers are facts. They are like as close to facts as possible. Like definitely there is errors in them, but there is no statistics or no prediction in them. This is essentially your A/B testing tool telling you that we tracked 6,000 visitors out of those 500 converted. And this is sort of any statistics is built over these empirical numbers. So why the empirical numbers come out to be important is that if the result of your test is unlikely, the first thing that you should look at, or like if it is surprising, then first thing you should look at is that whether it logically aligns with the empirical numbers or not. Because if there is a problem in empirical numbers, then you need to understand your pipeline of collecting data. But if the empirical numbers make sense, but the stats does not make sense, then it is likely that the problem lies in statistics. So empirical numbers give you that first point where you can start debugging and understanding why your statistics is the way it is. Now, the second level of statistics is the statistical averages. And what we do here is that we take the empirical numbers, we sort of divide them, and we get an estimated conversion rate. So if we have 500 converts out of 5,000 visitors, then what you are saying is that my conversion rate is essentially 10%. And here for 600 converts and 5,000 visitors, my conversion rate here is 12%. But I'll tell you now what makes this interesting. what makes this interesting is that level 2 onwards, everything is statistical. So all the numbers that you give have some sort of uncertainty embedded into them. So when I say 10%, then I'll also be looking at the number of total samples I collected. And from that, I'll be telling you that, okay, it's at average 10%, it's expected to be 10%, but there might be sort of some error to it, some uncertainty to it from the range of say 9 to 11%. So this is what statistics does. It calculates the median tendency and then tells you sort of the uncertainty in the estimate. And this aligns with that idea of the pendulum. So the statistical average is telling you that in what range sort of is the control swinging and in what range is the variation swinging. Now, this is our second level. So you'll get confidence intervals and the median value at second level. The third level is statistical uplift, which is essentially a combination of these two random variables. So the conversion rate on control and conversion rate on variation are two random variables. And what you do is you essentially subtract these two. So conversion rate of variation minus the conversion rate of control. And what you get is what is the likely uplift in your test. And here we have expressed uplift as relative to sort of the baseline. So the difference here is 2%, but relative to baseline, it is 20%. That's how it is usually expressed. Always it is expressed as relative to baseline. Now, the interesting part here is that uplift also has a standard deviation to it, has an uncertainty to it. So, which is essentially the sum up of the uncertainty in both control and variation. So the uncertainty in uplift is wider. So what uplift is saying is that maybe the control has a baseline conversion rate of 9% and maybe variation has a baseline conversion rate of 13%. So maybe at best, my uplift is around 40-45%. But at worst, maybe control has 11% and variation has sort of say 10.5%. So at worst, it can be below zero as well. Any questions? This is really nuanced statistical stuff that I'm trying to simplify. So if there are any questions or you are not able to follow, then please ask me right away. Wonderful. Finally, coming to the last level only tries to tell you if the area above. So essentially what this confidence around this uncertainty around the uplift is in the form of a bell curve, is in the form of a normal distribution in Bayesian statistics. And you try to see that what is the chance that this uplift is above zero. And when this chance above zero crosses 95%, you declare a winner. So this coincides exactly with this uncertainty in uplift going above zero. So this confidence interval of uplift, when it goes above zero, you have a winner. This also coincides with the fact that the uncertainty in conversion rate of control and conversion rate of variation, whenever it stops overlapping, you get a winner. So this is how these four levels of statistics are very beautifully aligned. Now, I want to highlight that this is the Bayesian system. And whatever any one of you might have read about p-values might be slightly different to this. But we'll discuss that in detail and when these are the same. So practically, they give you the same inferences. That is why I choose to explain it with the Bayesian framework, because it's easier to understand. The frequentist framework is much harder to understand. So yes, that's the four levels of statistics from data. Any questions on that? Wonderful. So I have one question for you guys, just to tell you the beautiful things that are confidence intervals. So confidence intervals are nothing but generally you see them for either conversion rates or uplifts. So confidence intervals are just like sort of your bar of the uplift. So you define, like when you define a 95% confidence interval, it tells you that 95% chance, essentially the value, the true mean lies in this area. Now you can read confidence intervals very visually and very intuitively. And confidence intervals directly tell you if you have had a winner or not. So my question here is that your winner cutoff is 95%. And what you are seeing in the current statistics is that your uplift is 20%, your significance is 93%. Which of these three are likely to be the case with confidence intervals? Like we see the first one where the confidence interval is entirely below zero. The third one, it is entirely above zero. And in the middle one, it is overlapping with zero. Yes. So I think people have gotten it right in the chat that it is two. And why it is two is that what I want to highlight is that whenever your confidence interval of the uplift is overlapping with zero, you won't have a winner then. Whenever it sort of crosses zero, you'll get a winner. So the interesting thing about confidence intervals is that the more and more samples you collect, the more and more they shrink. So if your uplift is anything other than zero, then theoretically, after enough samples, you will get a winner eventually. So yes. Any questions up till statistics? Then I'll move to Twyman's law. Great. Wonderful. So moving ahead with Twyman's law. So essentially, you should not think about deploying or disabling a test until and unless you have a statistical decision, because or you hit the maximum sample size of your test. So once either you get a winner, which is statistically significant, or you get a statistically significant sort of a loser, sort of a disabled condition, or you hit the maximum sample size, that's when you have entered the stage that you can now review the test and decide what action needs to be taken. And the interesting thing is that we like to, we have tried a lot to reduce it to a simple parameter that if anything is above 95%, you can call it a winner. But statistics does not work like that. Context matters quite a lot. And that's what I've been teaching a lot of experimenters, that when once you get a winner, that's when you're thinking scientifically and asking questions and scrutinizing the results start. So here I'm sharing with you 7 questions that you should ask yourself and analyze once you have gotten a statistically significant winner. And these 7 questions will help you decide that you should do one of 4 things in a test after you have gotten a winner. Either you disable the test, either you stop the test, or you sort of keep it running further, or you sort of replicate the test to confirm your findings, or if your findings are sure enough, then you deploy it. So these are the 4 things. Like in the next puzzle, I've mentioned these 4 things as well. These are the 4 decisions that you can take essentially. What you base these decision on are these 7 questions. There can be more, but these are the 7 that I have found out to confirm the validity of your result. So let's go over them one by one. The first thing that you need to ask yourself is the result sufficiently powered for number of visitors or not? So if you go by this method where you have calculated the sample size in advance, then you might get a winner early if you are running sequential testing. So one very important thing is that there are 2 types of testing. One is sequential testing, where you are allowed to calculate statistics on the fly and stop the test as soon as you get significance. The other type of testing is fixed horizon testing. The fixed horizon testing is that you decide a sample size and you do not look at statistics until that sample size has been reached. So generally today in modern A/B testing, we are moving more and more towards sequential testing, more so for companies who have lesser visitor quota to sort of invest into their tests. So I'm talking with the respect of sequential testing, and a separate webinar, I'll discuss sequential testing, its guarantees and everything in detail. So the first thing that you should ask yourself is that if your test was meant to run till 50,000 visitors, and you have say you have gotten a winner in say 5,000 visitors, then you should be wary about that winner. You should wait for that test to gather more sample sizes to see if the winner reverts. So the good thing about A/B test winners is that when they are genuine, the statistical significance goes on to become more and more stronger. But when they are bogus, when they're false positives, then it is highly likely that you invest one more week into the test and statistical significance retraces back. So the first thing that you should ask yourself is that how far you are from maximum sample size. If you are very, very far, then you should consider running the test longer to confirm your findings. The second thing that you should ask yourself is the result surprising based on what you expected? Now, this is very tricky, and I'll tell you why. So, suppose you are running a test on a metric that regularly shows an uplift from, say, 5 to 10% or 15%. And suppose compare it to another test where you have a metric that regularly shows you only a 1 to 2 or 2 to 3% uplift. Now, suppose you have gotten a 5 to 6% uplift on this test. In case one, where you have been regularly seeing these uplifts, it is much more believable and you don't need to run this test longer. But in case two, where that kind of a test and that kind of a metric generally shows a very small uplift, and suddenly you see a very large uplift, now there is a very high chance that it might be fluke. So you need to have this in mind, that what is your prior observation and what did you expect. If your results are surprising to expectation, then you should definitely consider running your test longer to be more sure. So if you were taking a winner at 95%, then you can say that, okay, this is very surprising, let it reach 99%, and then I'll take a call. Now, the third thing that I want to, the third question is, how many goals, variations, and segments are you looking at? Now, this is a very interesting counterintuition about statistics. The more numbers you see in statistics, the more chance that you by chance get a winner as a false positive. Like you just get a winner by chance. So suppose I create 20 variations in my test, and then I'm looking at a winner at 95%, then it is very likely that at least one in those 20 variations will give out a winner. So what you really need to do is that you need to ask yourselves that how many variations were you looking at? How many segments did you divide? Maybe you try to divide your data into mobile, into desktop, into tablet, and out of these three you found one to be winning. And how many metrics did you look at to find the winner? So one very important thing is that in the ideal scenario you should have only one primary metric on which the decision is based. So you should not base your decision that I have these four metrics, if any one of these go up, I'll declare it to be a winner. Now the thing how to tackle this is that if you are actually seeing more than one case, then you need to divide your false positive rate by that much. So suppose I'm looking at 5 variations, and I just tried out 5 variations of my idea, and now I got a 95% winner, which was like 5% false positive rate. Then essentially I divide this 5% by 5, which is 1%. So what I say is that if I'm looking at 5 variations, then I'll consider it to be a winner when significance reaches 99%. So this is one for only correction. It is slightly mathematical. If anyone has a doubt about it, just ask me. After this webinar, we'll have a 15-minute question answer session. I'll explain. The fourth question is that if you are running sequential testing, you should ask yourself. So if you are looking at your results intermediate into the test, if you are peeking into the results, then your statistics should be sequentially correct. There are 2-3 methods to do this that different vendors give you. Most of them are all right. I've done a trade-off analysis of them for a separate webinar, but you should ensure that sequential testing statistics should be properly corrected. Ideally, sequential testing stats are more conservative than your fixed horizon stats. So if by simple statistics, if by traditional t-test you are getting a 90% p-value or significance, then with sequential testing you'll get something lower than that. So ensure that your test is sequentially corrected. The fifth thing that you should ask yourself is that are there any potential data issues? So 2 of these that are commonly done is a sample ratio mismatch test. A sample ratio mismatch test is sort of like a thermometer for a lot of data issues. So you can run an SRM and you can basically debug if there is a data issue. You can also look at outliers in your test, and you can see that if the winner that you've gotten is due to some very large outlier or not. I'm not going into details about this right now. We'll be dealing with these in another webinar on dealing with high frequency, high fluctuation metrics. So, but you need to check for potential data issues. Finally, the sixth question is very interesting, and there is a puzzle for it also. But this is slightly nuanced, and you can do this only if you have a lot of visitors with yourself. So say you have gotten a 5% uplift in your test. you can divide that data into segments across different segment types in your audience pool, and you can try to see that how uniformly is this uplift distributed across different segments. So suppose you have gotten a 5% uplift, and you break it down by desktop, mobile, and tablet, and you try to see that is the uplift nearly 5% on all three, or maybe just very high on desktop and very negative on tablet and phone. That also sort of gives you an idea of how confident your test results are. And finally, I see question 6 being asked a lot, but it often feels like people are looking for some good news in tests that did start breaking out results. Yes, you are right. You are right. It should not be done to find one segment that is giving the uplift. It should only be done to confirm an uplift in the overall data set. So it is definitely right. Question 6 is related to question 3, and question 6 can sometimes be misleading as well. So there needs to be a solid framework to so that you are not p hacking. And also you are right there, Derek. I think these are nuances that need to be taken care of. Finally, question number 7 is how often do you get winners in your A/B test? Now, this is a very important thing that if you are running more bogus ideas and very few good ideas, the chance of a false winner increases. And this is very counterintuitive. But if you are running more good ideas, so if you have, say, 30-35% good ideas, then the chance that your winner is false will be lesser. But if you only have, say, 5 to 10% good ideas, then you need to be very conservative with your false positive rates. So the chance of your false winners being like sort of bogus increases. So this is the seventh question that you need to ask, which is essentially you need to estimate what would be the rough winning rate in your overall experimentation journey, and that should guide that what is the chance that your tests can be bogus. So that is the seventh question. I am not going into details for it. Okay. I have some questions here. Arnav asks that for question 6, if you have randomly assigned the variance to treatment and control without any biases, shouldn't the effect expected to be uniform across the population? Yes. So Arnav, you are very right. It is expected to be uniform across the population, but it is generally there are two problems that happens. If it is expected uniformly across the population, then it is very good. Then that means that different population segments are responding similarly to the change. So the change is very much to be reliable. The uplift is reliable. But there are two problems that happen, that sometimes the metric itself has a very high variance, much more than statistics has estimated. In that case, when you divide by segment, you see different changing uplifts on different sites, which suggests that the metric was much more random. There's someone wants to ask something. Interesting. Sai, I'll take your question.
I see.
Yeah.
Yeah, I see it happen, Ishan, and I'm not quite sure how I feel about it, because I can see where people are coming from.
Yeah.
But
You see it happen in the sense like the variance and uplifts in different segments.
oh no, sorry, I thought you were asking about my question. Sorry, beg your pardon.
I'll just come to your question. Yes.
Yeah, sorry.
So is there a version of this approach where you have multiple metrics? But what is your view of a test where multiple evaluation metrics are all positive for one segment? Is this useful information that tells us whether the test worked for a segment? That's very interesting. Derek, I think I'll have to think about this a bit. My general advice is that you stick with one primary metric. Sometimes there are multiple diagnostic metrics, like multiple guardrail metrics, where people sort of divide this sort of a they do a Bonferroni correction on the false positive rate. The problem with multiple metrics is essentially two. One is that sometimes there is a confounding factor. The multiple metrics are representing the same thing. In that case, sort of you are getting only one signal, but you are seeing it multiple times. So you are likely to mistake the fact that you are sort of getting a very strong uplift, a very confident uplift, whereas there is a confounder that has been impacted. So it sort of confuses. The other problem is that when multiple metrics you have and some go up and some go down, then the test is not conclusive. So generally what is recommended is that if you have very like 3 to 4 crucial metrics, then you take a weighted combination or some logical combination of those and reduce them down to one metric for decision making. But for certain scenarios, we can definitely brainstorm and think around some ways if it is very, very important to have 2 or 3 metrics around it. Does that answer your question?
Yes, thank you.
Wonderful. So quickly moving towards the last part, and then we can just have questions. I just have 2 puzzles that might be interesting if you guys want to try out the Twyman's law thing, like the questions that I proposed. In this test, we have a winner that has arrived. We had the pre-decided sample size was 50,000, and we have gotten 5,000 visitors, and statistical significance is 98% at 20% uplift. Would you trust this result? What will you do out of the 4 options? Deploy, disable, duplicate, and keep running. You can assume that it was a sequential testing framework. Anyone wants to? So yes, I think the thing about this result is that based on how much was such an uplift expected, if it was expected and there was sequential testing deployed in place, then you can deploy this result. But if this is a surprising uplift, and 20% uplift is generally surprising, then even with sequential testing, I would recommend that you run this a little bit longer. The reason being that the number of visitors compared to the pre-decided sample size are very, very less. So it's a subjective call, depending on how surprising the result is and how is your answer for other questions. If this is the only one thing that is off, then you are still okay deploying. But if there are sort of like multiple things that are off, then you are better off keeping the test running. So yeah, that's question 1. Finally, the last puzzle that I'm asking, that's on what's the practical significance? Interesting. What do you mean by practical significance? Did I use that term?
No, I meant in that test. So you said we got a 20% uplift, but is that 20% practical for our business or not? Is what I was saying in evaluating whether you want to deploy or like keep running.
Yeah, so what I really meant was that if you have a metric, so if you have run the test on a metric and all past tests on those metric have only shown a 2 to 5% uplift, then this 20% uplift is very surprising based on past data. But if that metric sort of regularly shows you uplifts of 10, 15, 20%, then it is more reliable and more trustworthy, essentially. So your past domain knowledge on that thing sort of needs to be included in the final decision. Does that answer your question on practical significance, Anna?
Yeah, it does. Sorry, I was thinking from a different angle.
Interesting. Do you mean to say like practical significance in the sense of the Bayesian chance to beat control?
No, I was saying, let's say, if our practical significance here is 30%, for example, 30%, if we observe an uplift of 30%, which is practical enough for our business, then it would make sense to deploy this test.
Interesting.
Otherwise, even if it's 20% and significant, if it's because like let's say we need to build out certain things for this test, from that angle, essentially.
Yes, definitely. So you are thinking that right in the sense that some things, even when deployed, if they have a cost associated to it, so you don't need to deploy every small change that doesn't cover business costs. It is something that we talk about in region of practical equivalence. So that's a entirely different term and a new concept. So I did not mix it up here, but we can discuss it offline if you have questions around it. And actually that sort of a thing can help you sort of disable non-potential variations early. So yeah, so if you're getting a small uplift, whereas there is a large cost to building that thing, then you can stop the test early.
Got it. Thanks for explaining, and sorry for taking this off topics. Yeah.
No problem at all. No problem. So finally coming to this last puzzle, and this is on post segmenting and how I like to See it? So in this test, you have gotten an overall uplift of 5%, which is 97% significant. So you broke it down by different days of the week. Assume that there was enough data in every day of the week as well. And what you are seeing here is that uplifts on different days of the week are fluctuating between a positive and negative. What will you do in this test? Should you deploy purely looking at 5%, 97% significance? Should you keep running it longer? Should you disable? Should you duplicate? And there is no right answer. It's a subjective call. Yeah, right. Yeah, that makes sense, Tarek. In your case, it definitely. So, in fact, Tarek has raised quite a interesting point here that in the news business, and if the change that you have made is sort of related to the days of the week, then this is very plausible. Yes. Apart from that, like the answers of keep running that Ulysses, Arnav, and Patricia have given are definitely right. I would have gone for that. The reason why I would keep running this test is because looking at these uplifts, it seems that there is still a lot of variance in the results. And the only way to get over variance is to add more sample size to your test. So you can add more sample size in hopes that maybe this variance falls down. But you need to keep this in mind that maybe this variance is just indicative that your metric fluctuates a lot. So I want to highlight that even though the statistical procedure takes into account the variance, but it also assumes that your metric is normally distributed, which a lot of times it is not. Sometimes metrics have a lot of outliers. They have a lot of variance that even stats cannot track. So in that case, it is very typical that you'll see sort of fluctuating uplifts in different segments. And you should be wary about the uplift that you are seeing in such a test. Finally, this was the last slide. So I'm all up for questions that anyone